This lecture begins the last part of our class, Symmetry, Structure, and Tensor Properties of Materials. In this lecture, we will introduce tensor properties of materials. We have built up from symmetry arguments to then talk about all the possible different point groups and then space groups that could be constructed in both 2D and 3D. Then we went through at least one easy way to see how you can populate these crystal structures is look at the atoms and their coordination number. We talked about how with hardball model from ionic materials we can kind of populate these crystals. And then finally here we're going to represent the overall macroscopic properties with tensors and talk about how symmetry affects them. So let's just start with just a little introduction here. So the kinds of properties we'll be talking about, of course, the classic one, which is often used as tensors are used for, are mechanical properties. The other very, very, very common one are electronic properties. So you can think of the mechanical properties. Of course, there's stress, strain, etc. Mechanical properties, you have conductivity, piezoelectricity, etc. So these actually two general categories are really the dominant categories we typically look at. But there's also not single-valued properties. A good example of that is the color of a ceramic. If you look at a ceramic material, it can sometimes be, let's say, a reddish brown color. That's a combination of both the actual electronic properties combined with mechanical properties that are displaying themselves through a surface texture due to some sort of processing. So you could look at those with a tensor, although they're not really connected independently down to the crystal level. And so that's why we're going to look at what we're calling single-valued properties, things directly related to a single property directly related to the crystal structure that is composed of atoms. So our single-valued property. And so we're going to have to define property, and it's a response of a material to a specific change in a condition that relates independent and dependent variables. So, for example, we will have generalized displacement and a generalized response. is one way to look at it. So one can think about temperature as a force and entropy as a displacement. You can think of electric field, of course, the displacement vector itself as displacement, and you can think about, I have to be careful with our use of sigma here. Sigma here means stress, and a little epsilon, which is strain. So these are all examples of forces and their displacement. So those are materials properties. I apply a force and I get a displacement out. Now, it turns out that these are very common relationships that I show here. It turns out that the product of these is energy. So these types of tensor properties, these types of force and displacement are called conjugates because their product is energy. Okay, so you can say that's great, but why do I need to think about these in a tensor, which a tensor really represents a three-dimensional view of the crystal properties. And there's some classic type of examples. One is I have a relatively new field since the 70s and 80s. I can have these polymer segments and have them in a dense array where electrons can hop this direction, but then they conduct through excitons along this way. And if these polymers can be stretched through mechanical forces into particular orientations, you can imagine easily that if I were to put an electric field here, that the current may actually prefer, on average, to go this way. Because remember, we're looking at a macroscopic force and a macroscopic displacement where these very microscopic effects are operating at a much lower level. And so the electric field can be going this way. Current could actually be flowing this way. And to make it even more confusing, if I put electrodes on either side and I actually measure J parallel, it is even a more reduced set, because first of all, it's confusing enough that I put electrical field in this direction and current's actually flowing this way. But now, out of that current, I'm actually only measuring the current along the electric field. And this is a very common problem. And after we develop some of our tensor foundation, this is one of the things that I actually want to get to in the class, because it's a very practical thing. You kind of make a slice of a material. For some reason, it's always in a particular orientation, and other things can be at angles to it, but you actually measure properties in one dimension with one particular force. And so this is really one of the main, very useful properties of tensors, which is to relate such an experimental situation to what's happening inside the crystal with a reference frame that we know inside the crystal. Another example that is often used to show this are things that, of course, have very large asymmetries in properties and directions. So, for example, you can make something called pyrolytic graphite, and you can't. It's like the hot topic of graphene. But in the old days, we used to call it pyrolytic graphite, where you actually build up the first few layers that people talk about through a deposition process, and everybody's been looking at those now. But if you keep on growing on a substrate like that, you'll get something that is analogous to polycrystalline, where you have these sheets that have nucleated and they grow on top of each other very well, but they don't grow over here very well. And so you actually end up with, and you might have seen pyrolytic graphite crucibles. You actually can machine this stuff, and it's real material. It's just that it has a particular form because it was seeded always on a substrate, and so you get these regions where it was seeded, they come together. And so it's almost like a single crystal of graphite, except that of course you've got all these regions in between that are kind of messy. So one of the amazing properties here is, if you look, thermal conductivity. If we were to take a candle and heat this up from below, you can take a cotton ball and put it on the surface, and you could put a cotton ball over here at the edge, and of course with the gigantic asymmetry and property that we're talking about here, what's going to happen is that of course this thing bursts into flames, and this thing sits there as happy as can be. And that's because these little layers of graphite, right, the thermal conductivity J in this direction is super high, where of course across this, where the bonding is very weak, it's very difficult to transmit phonons, and it's very low. So another example of really, if I want to look at these materials in general, I can't just always be thinking about one dimension. Now, of course, in this case, ironically, the asymmetry is so great that if I'm interested in this direction here, I can pretty much make some assumptions usually and show, I can just assume all the heat is flowing in one direction, and it reduces to a one-dimensional problem. So this is why tensors are actually not needed a lot of the times, is that we have situations either from sample geometry or from the fact that the crystals don't have really drastic property changes of different directions, that a lot of times you can reduce things to one-dimensional problems, either because it's like kind of these two extremes, either that it doesn't matter too much, and so you can kind of treat the thing as not having a high anisotropy in properties, or the opposite, where it's so high in anisotropy you only need to worry about one direction, for example. But there will be cases, in many cases, where we're in between, and so we need to think about more than just the one-dimensional view of the property. Now, before we move on to start to build up our toolbox for looking at tensor, I want to just go through some simple assumptions we're going to make. First, each component of a property vector is a linear, and this is the key thing, combination of every component of the applied vector. So it's a linear response. So if I have, let's say, and this is the generic case we're going to look at, if I have some uh, application of force through P, let's call it, and I have some response, Q, then Q equals AP, and we're assuming that there's some connection between the two, and that components of P are broken down, and through this A, they're linear in Q. Okay, and it turns out there's a lot of properties. There's a couple of assumptions here. Is that a P is sort of small enough that we stay in a linear regime. What often happens in materials properties is that when these get very large, there's a huge force on something, then the displacement starts to show non-linear behavior. And then, of course, you can't just do a lot of things we're going to do here where you assume that they're linearly related in all ways. And, of course, many interesting properties occur with, especially if you think about optics, nonlinear optics is where when you apply electric field, you start to get properties that depend on the square of the electric field and the cube of the electric field even. And these nonlinear components end up giving you very important properties, like, for example, the ability to have a green laser pointer right now, which is a frequency doubled you use a frequency doubled crystal to take a longer wavelength and actually bump it up to a higher energy, and that's only done through a non-linear effect in a crystal. So it matters. So that's one example. So we have, I'll use green just because of that example. So we have non-linear optics. In magnetic materials, we have magnetic saturation. So if you recall, we have magnetization is magnetic susceptibility times the magnetic field. And this is fine, if you recall, for some range of things. Let's say a ferromagnet, right, is a good example. So for a ferromagnet, if I look at H versus M, I might have this down by the origin looking very linear, but then when it comes up, it can roll off. Then when I go back, I even have hysteresis. It becomes linear somewhere else, and I can go forward, and I can have this loop behavior. And yes, for some range, it stays here, but then actually it can go into a completely different mode to never come back unless I do something to reverse it and try to come back down here. So there is a regime where this is okay, but then I have magnetic saturation, which is this, and then I have hysteresis, which is this, and these all require more complicated treatment because you can't just split up the response into little tiny vectors of these guys and they're automatically going to linearly be related to adding up and contributing to that. And then finally there's, many examples, but electrical breakdown's another one. We're going to talk about conductivity. Where, J equals sigma E. For a wide range of electric field, I have current flow and it's proportional to the conductivity sigma is the constant of proportionality. But when I get to high enough electric field, all of a sudden this breaks down and then this linear relationship doesn't hold. I gave you, I mean, there is another example, famous example, which is related to connectivity, is inside J, I can look at a certain number of carriers times their charge times their, times their velocity. And so, you know, this y-axis can be thought about current, and the relationship is that electric field and velocity is related by mobility mu. And so it's ohmic, but then what happens is that there's also a saturation typically. And so that's called velocity saturation, but it's essentially current saturation. So it's like magnetic saturation. So in this case, there's no hysteresis, of course, but same kind of thing. So these are the limitations in which we are working. So we'll stop there. Hopefully you can see that we are in need of thinking about three dimensions to understand materials properties and connect it to crystallography in a lot of cases. In extreme cases or incredibly bland cases, homogeneous isotropic cases, we tend to drop and think of linear because it's easier. Think of only one direction, a linear problem. Here I'm talking about that when we think about three dimensions, the vector notations and the relationship between the response and the force are assumed to be linear, and I talked about some limitations of that. But ignoring these limitations, let's go on in the next lecture and build our foundation for using tensors to represent three-dimensional materials of properties.